All right, welcome to chapter 8. This chapter, you'll notice it's not called momentum or anything like that, or collisions or any of that. Although momentum will play a big role in this chapter. So this is the first chapter where we're seeing systems comprised of more than one object. So everything before this chapter, it's been a point mass, and we've just focused one point mass at a time. So like something in projectile motion will undergo parabolic motion. But if you throw if you throw a person off a cliff, the person is not just a point mass, right? So maybe it's not a nice parabola, but there is a sense that there is one special point called the center of mass that would follow the parabolic trajectory. When you have a system of particles, you can a lot of times you can treat it as a single particle at the center of mass, but we need to see what sort of assumptions go into that and why we can treat it that way. So that will be the first couple sections, and that'll bring us into looking at a multi-particle system will require introducing this thing called center of mass, and this will let us make a statement involving multiple objects. Systems with more than one mass in it. And then, once we develop some of the formalism, then we can look at problems involving, we'll also define momentum and then look at problems involving collisions and explosions where momentum would be conserved. So we also want to understand when momentum is conserved and when not. Okay, so you look at this problem, it's a center of mass problem, but first we need to see what we mean by center of mass before we look into how to calculate some center of mass things. Okay, so your book, so I'm going to do something pretty similar to what your book does. So I'm going to focus on a system of three masses. So call this M1, M2, and M3. So this is my system. Right, so I'm going to so these three masses are my system. Anything outside of it is external. So anything inside is internal to the system. Anything outside is external to the system. Okay, so we're looking at just a couple masses just to see how this works, but you can easily generalize this stuff to n particles. Okay, so Newton's second law is true for each of the three masses. Okay, so I'm going to write down, so for each mass, the sum of the forces on m sub I is equal to that mass times its acceleration, times a sub I. So already I'm going to replace this a, and I'm going to call this r double dot. So we're using this convention where a dot means a single derivative with respect to time, and two dots means two derivatives with respect to time. Okay. So I'm freely going to go back and forth between writing that and writing acceleration. So just to warn you, that I mean the same exact thing by these two. I could write either one. Okay. So we're going to write down three equations, and for the first mass, for example, M1A1. So for the first mass, I'm going to split up. So I want to write down all the forces that are acting on M1. Now I'm going to split this into two different forces, internal and external. Okay, so I'm going to add up all of the internal forces on M1. And I'm also going to add up all of the external forces on M1. So, sorry, these subscripts, they're a little hard to read. I and E. Okay, these are vectors. So the internal forces. So remember, we said that anything inside our this dotted line here, anything within the system is internal, anything outside of it is external. So in other words, if M2, there's a gravitational force between these two masses and between M1 and M3. So there are a couple gravitational forces on M1. Those would be internal forces because it's M2 that's pulling on M1 and it's M3 that's pulling on M1. Okay, so those would go in the internal category. If if there was a fourth mass out here, because that's outside of the system, pulling on M1, that would count as an external force. Okay, so anything within the system that pulls on M1 or pushes on M1 is an internal force. Anything outside of that is an external force. So we can write down the same equation for M2 and M3. So sum of the internal forces on M2 plus the sum of the external forces on M2 is equal to M2A. Sum of the forces equals mass times acceleration. And we're not saying that these things have to be attached or anything. So the acceleration of M1 and the acceleration of M2 are two different quantities, right? We're not using the same acceleration there. And then we can write the same thing for the third one. And you can see why I limited it at 3. I don't want to imagine doing this 10 times and just writing this over and over again. It wouldn't be fun. Okay, so what I'm going to do now is I'm going to sum the left-hand sides of all 3 equations, and I'm going to sum the right-hand sides of all 3 equations. So the sum of all internal forces plus, and that's the sum of all internal forces on any mass, right? The sum of the internal forces on M1 plus the sum of the internal forces on M2 plus the sum of the internal forces on M3. And this is the sum of all external forces. This will be the net external force is equal to, and it looks like we just have a sum of the masses times that mass's acceleration. So this is, this sum symbol is just a shorthand, and a lot of times we're sloppy in physics and we don't write down, like here technically it would be I, the index, would go from 1 to 3. But it's understood, whoever writes this down says, oh, the person will understand that, the I subscript is referring to a different object, and we're going to sum over all those objects. So maybe you'll see a sum over I right here. But they might not put the exact limits on it. Now your book does this for only 2 objects, but I'm just showing how quickly this gets to be kind of complicated. But no matter how many objects you include, this term right here is 0. And it's 0 because of Newton's third law. Okay, so just looking at gravitational forces, let's look at all the internal forces. So if we look at M1, there's 2 internal forces on M1. There's one from M2 and one from M3. And then if we look at M2, there's 2 more. There's, there's one more. We've already included the one from M1. So basically there's this pair, and there's this pair, right? Those are the 3 pairs. But there are 6 terms that appear in this right here, in the sum of the internal forces. So like there's a force on M1 from M2 that's pointing up and right, but there's a force on M2 from M1 that's pointing down and left, and those 2 will cancel. So for every pair here, there's a Newton's third law pair where both of those Newton's third law forces are on masses that are within the system. And so in the sum, we're including both of those just by definition. So this is why we're separating out the internal versus the external ones, because the internal ones are all going to cancel as long as we add together everything within the system. Okay, so from Newton's third law, all of the internal forces will cancel. And so we can make a statement about what happens to the whole system just by looking at the external forces. So the sum of the external forces, and the external force can act on anything within the system. So something external here, if it pulls on M1, pulls on M3, pulls on M2, any of those would be an external force. So if you would have to add all 3 of those together, right? So you sum up all external forces that are acting on anything that are acting on the system. And I'm going to write down, so I'm going to multiply and divide by the total mass. So I have M total, and then we have sum of M sub I, A sub I, divided by, and we're adding up all the masses. So I multiplied and divided by sum of the masses. So in other words, M total and sum, so this thing and the denominator here are the same thing. So just multiply and divide by that same thing. So this is a kind of acceleration. So there are three accelerations going on, one for M1, one for M2, one for M3. But this is just a single quantity. Okay, so each A is different, but as long as you add them, you take a weighted average of the accelerations weighted by the mass. This is another acceleration, and it's the acceleration of the center of mass. So we got to be careful with the definition. We're going to define something called the center of mass. So the center of mass, we're going to define with this and with, eventually we want to be able to explain this. The center of mass is a sum of where the particles are, and so it's a weighted sum, weighted by each of the masses. So the bigger the mass of an object, the more important that term is to this weighted average. And then dividing by the sum of the masses, just so that we get units of position here. And you'll see because the masses are constant, you can just take a derivative with respect to time. So once you've defined this thing, it's a well-defined thing, the center of mass, and so velocity is well-defined. You can just, when you take the derivative, because the derivative is a linear operator, you're acting on every term in the numerator, and the mass, the derivative can just act directly on the position vector. So the velocity of the center of mass is a weighted sum of all of the velocities of the object divided by the total mass. And then same with acceleration. The acceleration of the center of mass is a sum of all of the accelerations weighted by the mass. So, and that's exactly what this term is. So this is the acceleration of the center of mass. Okay, so the main equation that we're getting to in this video is that the sum of the external forces on a system is the total mass of the system times the acceleration of the center of mass of the system. Okay, so what we're saying is that we can treat this system, remember we started with three objects, we can treat this system as one object. All right, where should we put that object? What all this is saying is that the natural choice of where we should put it is the center of mass. So imagine M3 is much, much more massive than M1 or M2. Maybe the center of mass is like right here. So this would be the center of mass if M3 was really big compared to M1 and M2 was big. If M1 was a lot bigger than the other two, it might be a lot closer to M1. If all three were equal masses, it would be somewhere in the middle. It'd be somewhere in, closer to the center of that triangle. Okay, so the center of mass is, if we were to describe the location of the whole system, where would it be? It would be the location of the center of mass. And this thing, as the particles move around, this center of mass can move around. And that's exactly what this equation is describing. Okay, if we're going to treat the whole system as one object, then there's a F equals ma. It's like generalizing. So this equation generalizes Newton's second law to systems of particles. Okay, so you just have to, so you can ignore all the internal forces. You just look at what's pulling on the system, pushing or pulling on the system from outside the system. And the sum of the forces equals the total mass of that system times the acceleration of the center of mass of the system. Okay, so we showed how to think about how Newton's second law generalizes to systems of particles. Okay, maybe, so we haven't seen why it's useful quite yet, but at least we're understanding that maybe center of mass has something to do with it. Okay, so your book starts off by saying, oh, in section 1, oh look, the internal forces cancel. Okay, so your book starts with just talking about it in one dimension. They're equal and opposite from Newton's third law, so I can ignore that. And then introduces the center of mass. So see exactly this right here. So for two particles in one dimension, this is the weighted average. This is what that equation looks like. So m sub I, x sub I, m1, x1 plus m2, x2 for two objects. And then the capital M would be the sum of the masses. So if you have two particles of equal mass, the center of mass is exactly halfway between them. That's what your book is saying right here. Right? For three particles, you would do this. which can be generalized to n particles by replacing the 3 by n in the sum. So you just sum over however many particles you have. Okay. That's basically all your book is saying. Then saying, well, this works in more than one dimension as well. Now, I wrote down this vector equation. So let me go back to that. So our center of mass, let me remind you, was 1 over m total, or the sum of each mass times the position vector of that mass divided by the total mass. So you might see it written this way, you might see it written this way. M total, or capital M. Now this is, you got to be careful with vector equations because it's a lot of information contained all at once. So we're using R because we want to talk about the whole position vector in multiple dimensions all at the same time. But really this is multiple equations all at once. So this is saying that for the x coordinate of the center of mass, so suppose like you have a coordinate system for these 3 particles, x, y, and you know where the origin is. Say the origin's right there. So that like M3 has negative x and negative y. In order to find the location of the center of mass, you have to know its x coordinate and its y coordinate. Okay, so you can just take the x coordinates of M1, M2, and M3 and do the weighted average of the x coordinate to find the weighted average of the x coordinate of the center of mass. And you can do the same thing with the y coordinates as well. So it's saying that in order to actually compute the center of mass, you can do each component separately, okay, which is a lot easier to work with. So this is 1 over m total, sum of each mass times its x coordinate. You sum over however many particles you have. And then same for the y. And same for the z, if you're working in a 3-dimensional problem and you have to do 3 of these. Okay, so this equation for our center of mass is really 3 equations in one. Right? One for each component. Another way that this generalizes, so your book just kind of goes on and on and on. So I'm going to talk about, so you'll see this integral sign, so I want to talk about that. Before I do, I want to mention that like you have 2 blocks here. So you can do the center of mass calculation in steps. So like each block, each of these 2, let's not talk about 3-dimensional blocks, let's say 2-dimensional sheets. For each of these 2-dimensional sheets, they have their own center of mass, like this 1 and 2 in the diagram, which if the mass is spread out evenly, if the mass is spread out evenly, then the center mass of sheet 1 is right in the middle of that one, and sheet 2, the center mass of that sheet is right in the middle. And so the center mass would be, you can just do the weighted average of those 2 things, right? So you don't have to split up each of the 2 blocks into infinitely many pieces and then do an infinite sum or an integral. If you can simplify, if you can take an object and split it into chunks, and each of those chunks have an obvious center of mass, you can just deal with those, and then it becomes a simpler problem. So it looks like here, looks like sheet 2 is a little bit more massive than sheet 1, because the center of mass looks like it's not exactly right in the center of those 2, right? Looks like it's a little more towards the second one. That's indicating that the mass of the second one might be a little bigger. Okay, now in a math class, in calculus, you learned how to generalize sums to integrals. So I want to tell you how these formulas would change if you had a continuous mass distribution. So for continuous mass distributions, so in other words, you don't just have a few point masses, but you have mass spread out over a length or a volume or an area. For continuous mass distributions, you replace this sum. So suppose you're summing over a position and then a piece of mass. Suppose we had the rod and we split it up into infinitely many masses. Right? If you looked at one of those tiny pieces of mass right here, if we split it into 1,000,000 pieces, 1,000,000,000 pieces, 1,000,000,000,000 pieces, that mass is going to get really, really, really tiny. So this is the infinitesimal here, dm. Let's say this is x equals 0. But the position of that mass would be some well-defined x value. Okay, so what I'm trying to say is that this sum becomes an integral over the masses. So the mass is the infinitesimal piece. And then the position of that infinitesimally small mass is just some finite, well-defined value. So we're not integrating m dx, we're integrating x dm. But this integral is sort of abstract, right? We would want to integrate over the mass distribution. So we want to integrate over the object of a x-coordinate times dm, which is abstract, right? You're used to, in a calculus class, you're used to doing an integral with some bounds of the integration. Okay, so in order to carry out this integral, what helps us is a measure of like the mass per unit length. Okay, so to actually compute this, and we have an example up above. To actually compute this, we introduce mass densities, the mass density. So if you had mass spread out over one dimension, suppose you knew that this rod right here, suppose this is just a rod in 1D, so we're not worrying about any area. It has total mass m and it has total length L. If that mass is spread out evenly, then you would have a constant linear mass density. And in one dimension, we use the symbol lambda for this. So this is mass per unit length. So in principle, that could depend on x, right? If it was more massive right here and then it gradually tapered off in mass, that lambda could change. But if lambda is constant, if the mass per unit length is constant, it's the total mass of the object divided by the total length of the object. Okay, who cares? The reason this is nice is if we look at this and we solve for dm, we could write dm as a constant times dx. And if you plug that into your integral right here, that is something you can actually integrate. Okay, so the linear mass density in one dimension, and this generalizes in multiple dimensions to surface mass density, mass dm dA, or volume mass density, dm dV. So replacing the dm in the integral with this will actually give us something we can integrate over. Okay, so this helps us actually evaluate the integrand, helps us calculate integral of x dm. Or, just in general, wherever we are, position vector. Yeah, I'll just write x dm. Okay, that might have been too general. We want to see how this works in practice, right? So let's solve our original problem here. And then I'll go back and I'll sum up this statement with an example as well with that. Okay, so we have a semicircular ring of radius r in the xy plane. We want to solve for the linear mass density and find the center of mass. Okay. So first of all, I just want to point out that you don't have to do more work than you absolutely need to. So what I mean by that here is that we already know the x position of the center of mass. Okay, because of the symmetry of the problem, and you want to use the symmetry of the problem whenever you can. From symmetry, the x component of the center of mass is 0. Okay, all the work that's required in solving this problem is finding the y coordinate of the center of mass. The center of mass is somewhere like right there. Okay, for any little piece of mass right here, there's another piece of mass on the other side. And in the sum, like sum of m sub I, x sub I, for every positive x value, there's another piece of mass at negative x value. So those two terms will cancel each other out in that sum. Okay, so from the picture, just kind of obviously, as long as the mass is spread out evenly over the length of the semicircle, the x component of the center mass is 0. The y component, that's not obvious at all. It's greater than 0 because all the mass is at a positive y coordinate. And it's less than y equals r. Only if all the mass was at y equals r would the y component of the center mass be r. So the y component we'll have to do a little bit of work to get to. But this is the first thing to notice. From symmetry, it's somewhere on the y-axis, the center of mass. Okay, let's actually solve the problems asked for. So what is the linear mass density of the rod? Well, it's going to be the total mass. So we're told to spread out, the mass is spread out evenly. So it's just going to be the total mass of the rod divided by the total length of the rod, which is pi times r. Right? The circumference of a circle is 2 pi r, but this is a half circle, so it's just pi times r. So it's just this, and it's constant over the whole rod. Now for the location of the center of mass of this semicircular rod, we already reasoned from symmetry that xcm is 0. We have to solve for ycm. So this is going to be 1 over the mass of the rod times, and then we're not going to do a sum because we have to split this into a infinitely many pieces along the rod. So this is going to be an integral of y dm over the rod. So we're doing a weighted average of the y coordinate over the rod, weighted by the mass. So this is m total, and this is lowercase m. Now lambda tells us lambda is useful because lambda is what will help us turn dm into something we can actually integrate over. So lambda is mass per unit length along the rod. So this is mass, and this isn't dx, this isn't dy, this is d arc length. mds, dmds. And the arc length is the radius times d theta. Okay, so what we can do is we can replace dm with r times lambda times d theta. And theta is something we can integrate over. Right? Theta will go from 0 to pi. So that's perfect. That is something we can integrate over. Okay, so the center of mass y coordinate is 1 over the mass of the rod. And we can factor, well, before I do that, so plug in dm is r times lambda times d theta. And now we can actually specify and say, well, we're going to integrate as theta goes from 0 to pi. Now in this integral, r and lambda are constant, so we can take it out of the integral signs. This is r times lambda over m. But y is not constant. So for every little piece on the semicircle, so for any little piece of mass that we're looking at, it has a y coordinate that depends on our angle theta. Sorry, let me blow this up a little bit. So this is my little piece of mass, dm. This is where that mass is, theta. So we need the y coordinate of that little piece of mass, dm. So it looks like that y coordinate is going to be, is it r cosine theta or r sine theta? Looks like it's looks like y equals r sine theta. So we're going to plug that in right there. So the y component of center mass is r, well, I won't skip any steps here. R sine theta d theta. So it looks like r squared over m lambda integral 0 to pi sine theta d theta. Now this video is already running a little long, so you can show that the integral there is 2. And then lambda we're going to plug back in. Remember we solved for lambda in part A. This is m over pi times r. M over pi times r. So it looks like our answer for where the center of mass is, it's on the y-axis and it has y coordinate 2 over pi times r. So remember we reasoned that it should be less than r and bigger than 0, right? The y component of the center mass should be bigger than 0 and less than r, and that's true. Like pi is about 3, so it's at about 2/3 r, a little bit less than that. So this makes sense, and you see hopefully the utility of introducing the linear mass density lambda. Okay, so I wanted to at least give you an example of a center mass calculation for a continuous mass distribution. Your book has a couple examples of discrete, so just adding up one or two masses. But I really want to go back to, so before I conclude the video here in a minute or two, I really want to go back to the main result of this chapter. The sum of the forces, and I want to remind you of why we were talking about the center of mass so much. The sum of the external forces on a system is the mass of the system times the acceleration of the center of mass of the system. So we're summing up the whole system as a single particle at the center of mass. And we showed why we could do this. Okay, so this is useful because, I mean, so what we've done so far, so one thing I mentioned, one example I wanted to talk about was that we talked about projectile motion before in this class. So imagine you shot something up, it's undergoing projectile motion, and then somewhere here it explodes. Like you have a firework that you shot, and it explodes into two pieces. So one piece shoots out this way, some piece shoots out this way. So you have two fragments. One piece is like this, one piece is like undergoing its own projectile motion now. So this is M1 and M2. The center of mass, so because that explosion is an internal force from the firework, there's no external, the only external force is gravity. And so the center of mass still follows this path. It still follows the parabola. So if you know where one of these fragments is as a function of time, you can compute where the second fragment is just by looking at this center of mass, which undergoes a perfect parabola. So this is also like if you shot a person up. Their center of mass, you know, even if this person's rotating, twirling, doing all sorts of stuff, if you had to sum up the whole person with one point, it would be at their center of mass. And their center of mass is undergoing parabolic motion. It's not until one of these masses lands that there is an external force. So once M1, for example, hits the ground, then the ground's going to push up on M1. So that's an external force that will change the center of mass. And then it's more complicated than just a parabola. But it's not until one of those masses hits the ground. Okay, that was a lot of content for one video, so I should end it there. So you'll definitely get some practice in computing center of mass. And then next video, we'll talk about conservation of momentum, and we'll start to use this formula. All right.